Allora, benvenuti a questo meeting. Thomas ci parlerà di Polyglot e ovviamente siamo tutti ansiosi di sentirlo. Prima Gianluca ci parlerà 2 minuti di Kamai, della struttura che ci ospita e lo fa ogni volta e per cui ovviamente vi ringraziamo tanto.
Sì, saranno meno di 2 minuti, spero di stare sotto i 30 secondi. Venini 42 è lo spazio, Kamai e Linkme sono le due società che si impegnano per fornire lo spazio in sé per i meetup. JUG è una delle community che abbiamo il piacere di ospitare, ovviamente siamo felicissimi che sia dei nostri, diciamo così. E niente, quindi lo spazio Venini 42, le due società che si impegnano per organizzare la sala e per anche tenere i rapporti con le varie community sono Kamai e Linkme. Io sono Gianluca, sono di Kamai, sono un programmatore. Kamai lavora tipicamente in Rails e Ruby, quindi Java non è una tecnologia che utilizziamo. Sinceramente non ci frega niente di ospitare community solo Ruby e Rails, ci interessa ospitare un po' tutte le possibili community delle varie tecnologie che sono in circolazione. Questa è un po' la descrizione di spazio e delle aziende che stanno qui dentro. Un'unica cosa che volevo lanciare lì, siamo in ricerca di risorse Java, quindi se siete programmatori Java, consulenti, qualunque cosa, contattateci. La mia mail è gianluca@mikamai.com, trovate comunque tutti i riferimenti online, per qualunque cosa comunque è gianluca@mikamai.com. Grazie mille e buona serata, buon divertimento.
Grazie. Okay, lascio la parola a Thomas. Dopo il suo intervento ci sarà l'estrazione di 2 licenze di IntelliJ, perché l'ultima volta ce la siamo dimenticata.
Sì.
E qua abbiamo gli adesivi invece che potete prendere liberamente di IntelliJ, JetBrains, Kotlin, PyCharm e WebStore. La parola a Thomas, grazie.
Great, thanks. Thanks for the introduction. I didn't understand everything. The most important stuff. So, I can this.
Oh, sorry.
I need to do like the slides.
Okay, if you are here, you can use the arrows or
That looks good. But yes, yeah, my name is Thomas Wuerthinger. I'm a research director at Oracle Labs. I work in Zurich. Right now we have a big research labs in Zurich that's currently growing. We're expanding there. And I'm managing the programming language implementation teams at Oracle Labs. And this talk is about our main project in terms of programming language implementation, and it's about Graal. I'll have to show you this slide for legal reasons, so you shouldn't buy the Oracle stock, no matter how excited you are about our project. And with that, I give you a quick overview about the project. So, Graal is a new compiler for the Java virtual machine. And so Graal can execute Java code, can execute Scala code, or any other language that's targeting the JVM. And on top of Graal, we have developed a system that's called Truffle. And Truffle is done connecting the JVM with dynamic languages. That was the primary focus of Truffle. We have 3 major implementations of dynamic languages on top of this system. One is for JavaScript, one is for R, and one is for Ruby. So I think in the beginning there was something about Ruby. This company here using Ruby a lot.
Yeah.
We actually hope that companies like this will in the future run their applications on the JVM. Like every other Java user group person maybe. But because we can actually provide a better performance for Ruby than compared to Ruby MRI. We can also provide better performance than JRuby, but I will later come to that. And on the very right, there is one more project that we recently started, which is that we want to have the JVM really to be the platform for all programming languages, and the set of programming languages that we're still missing were the ones that were targeting LLVM as their backend, which are mostly static languages like C, C++, Fortran, Rust, Go, and these languages for which there is an LLVM backend, we now also draw into our ecosystem by providing a dynamic execution environment for these languages on top of the JVM. I will later go into details there. But this is really the great vision of our project here. You want to run every language on top of the JVM platform, and not just the languages that are Java, or not just the languages that are compiling to Java bytecodes. But well, back to Graal, to the starting point, our starting artifact here. Graal is a new compiler for the hotspot JVM. It replaces the server compiler, and it is connected with the JVM via interface we call JVMCI. You can see that Graal is written in Java, so it's actually a Java application that is the compiler, and it's connected to the JVM via JNI interfaces. And JVMCI is actually one of the JPs that were accepted for inclusion in JDK 9. So when you download a JDK 9 early access release, you will have this component included. You will not have Graal included, but you can get Graal from GitHub. But this component, the binary modifications of hotspot are already included in JDK 9. And we also have a modified version of JDK 8 available for companies that want to try out the system already on Java 8. Because Java 9 is not yet released, and it will take some time for the adoption to ramp up. So therefore, we also provide a modified version of JDK 8 that can run Graal. What are the specialities of Graal, or why is Graal different from other compilers, or from other compilers in hotspot? Well, the first one is it's designed for speculative optimizations and de-optimization. And I actually have a little bit of a technical content of what de-optimization is, because de-optimization is maybe the single most important concept when in need of obtaining high performance for dynamic languages. And second point is Graal has some very aggressive high-level optimizations. Most notably, it has partial escape analysis. So it will be able to remove allocations even if an object escapes on certain control flow path. So the standard example is you create an object and you compare this object against, you make a lookup in the hash table, for example, and if you already find that object in that hash table, you do not need the object. So in this case, the allocation was not necessary. But if you do not find the object in the hash table, you add this object to the hash table. So this is an object that clearly escapes in one of the paths, because when it's not in the hash table, it needs to be allocated. But it does not necessarily have to be allocated for the comparison. And this is one of the cases where Graal can actually remove the allocation for the comparison and only allocate for the case where the object is not found in the hash table. And in general, the escape analysis, it's not only that Graal has partial escape analysis, it's also the case that its escape analysis is a lot more predictable and powerful than the current escape analysis in hotspot. Because the current escape analysis in hotspot is done by some pre-parse before the compiler sees the graphs. So it's done on the bytecode level. And we do the escape analysis on the compiler graph. So after we do all of the inline decisions, we can still do escape analysis passes. Graal is a very modular architecture. It's written as a modular Java application with applications like Eclipse or NetBeans as models in terms of defining clear module boundaries. So we're kind of prepared for Jigsaw and JDK 9 here. And well, I already mentioned it, Graal is written completely in Java, which makes it easier to maintain and a lower entry barrier, in particular for Java developers. So as a Java developer, you should have a very easy time understanding the compiler. And you can also actually debug the compiler in your Java IDE while your compiler is running your Java application. So also from the compiler itself, when there's a bailout in the compiler, for example, you get a Java static trace. Then this aspect of having the compiler written in Java has another very interesting implication, which is that it blurs a little bit the line between the user application that's written in Java, the user library that's written in Java, and the compiler that's written in Java. And what we imagine here is that in the future there will be more potential user libraries, for example, having their custom compiler faces and hooking them into the compiler. And this is actually possible because you can just extend Graal by having your own compiler face written in Java and targeting some aspects, like targeting your own application with some knowledge that maybe a normal compiler couldn't have. Yeah, well, we use Graal, of course, as the first test case for Graal itself, because Graal can actually compile itself. So, that Graal is written in Java has for us one disadvantage, which is that it's taking a little bit longer to start the JVM, because Graal itself is warming up on top of the client compiler. So when you start the JVM, there's the client compiler as the first tier, and the second tier is Graal. And Graal itself is only compiled to the first tier level by client compiler. But this means that in the first couple of seconds of an application run, you have a little bit of a disadvantage because you're compiling. But yeah, the main targets that we are, like, our main target for all of this work is server-side applications, so long-running server-side applications. We're not targeting here with our work client-side applications. Also, we have something that could be very embeddable, but I will later come to. So I will want to talk a little bit about the optimization, why it's so important. So when you have a static, when you have a compiler control for graph, then one of the more important compiler optimizations is actually to straighten out that control for graph. And the reason is that this is one optimization that's similar to inlining, is feeding all other optimizations. Because when I'm at this block and I know where I was coming from, I can optimize this block in a better way. Because I might know that the variable x is like assigned 1 here and 2 here, but I don't, and at this point I would like to know where I was coming from in the control flow to reduce x to a constant. So the way static compilers try to achieve some of this is to just explode the control flow graph. So on the right side you can see here some control flow graph explosion that's basically reducing all of the merges and duplicating all of the blocks, such that there is no more merge point. Right? And what you can see, even for this small trivial example, it gets very big. It gets very huge because it explodes. It's like exponential in the number of merges. Right? So therefore, it's not very practical to do this in an ahead of time compiled manner. But what we do instead dynamically is that we profile which path is actually usually taken by the application. And once we find out that because for a particular application it's actually likely that some paths are never taken, and then we can compile only the path that was actually taken by the application, and we can for free reduce the control flow merges, improve the code quality. But we still need to have these exit points, because while we think this path will never be taken, it is not actually guaranteed. So you need to have the backup here. And this type of profiling and this type of optimization is really interesting for Java, but it's even more interesting for dynamic languages, because for a dynamic language, one particular operation can be, if you actually draw out the possibilities that this operation can do, can be very big. Like if you have a JavaScript plus, for example, you have to first check whether the left is a string, or the right is a string, or the right is an integer, or it's undefined or null, or whatnot, or whether it's a property lookup. So for one particular operation in JavaScript, the tree, the control flow tree of the semantics of the operation is very big. But in one particular JavaScript program on one particular place, you actually have very often only one very small subset of the semantic used. Okay? And this is why for things like JavaScript or Ruby, it's even more important to do this type of profiling and pruning. So the optimization itself is then a fairly complex operation, which is thankfully done by the JVM under the hood. But it's still interesting to maybe understand it approximately how it works. So the way this goes is that when you have an actual method compiled, it's not just one method that's compiled, it's multiple methods that are inline compiled, right? Because in the optimized code you have inline, in interpreter you don't have inline. And then what is maintained by the compiler and by the VM is a mapping between every single machine code location in here that can trigger the optimization and the values on the stack that need to be reconstructed when the optimization happens. So in each of the locations that the optimization can happen, we would have a list of methods that need to be reconstructed on the right based on the inlining. So in this case, I was inlining F2 into F3 and F1 into F2. So basically, those three methods on the stack at the current point in time. And I need to reconstruct all of the values of local variables of these methods at a specific point. So this is a fairly complex operation. It works on in the hotspot VM as one of the first VMs that actually do this type of operation. And nowadays, this type of operation is also done in the VMs like JavaScript VMs, for example, in V8 or SpiderMonkey. All of the Facebook Hack VM or Python Piston VM. Nowadays, every major Silicon Valley company has its own replica of a virtual machine, and they actually look kind of a little similar. But in the end, originally the technique was coming from Self, actually. You might still know the Self system from somewhere like the 80s. And then it was one of the major differentiators of hotspot. So, but the main power of the optimization lies in the fact that the compiler can kind of assume that this point here is really a true exit, and it never merges back into the compiler's code. So the compiler can this way say, like, I don't care about this branch, I will exit to the interpreter, and from my point of view, I'm never coming back. There is something like when you will come back into optimized code is either at the beginning of a method, because if the method is compiled, you come back. And there's a second point, which is on stack replacement, which is kind of the counterpart to the optimization, which is when you are in a loop in the interpreter, you can also jump into optimized code. Because if it's a very long running loop, you might not want to wait until the loop is over until you jump to your optimized code. Yeah, so I was talking about Graal, and I mean, in the end, all that matters about a compiler is its performance, or the performance it gives on the code it produces. Particularly for a server environment compiler, it's mainly about the performance of the code it produces. And this is the approximate picture we have right now. It's very rough numbers. It's kind of the executive summary of Graal performance. And right now on Java, we can be a little bit better than C2 in some cases, but overall it's at the moment a wash. But we think we can further improve on that. For Scala code, the picture is actually already different. For Scala code, we can on average provide better performance than hotspot with server compiler configuration. And the main reason for that is that our escape analysis and our inlining heuristics are better for modern type of Java patterns, like that have a lot of closures in them, have a lot of allocations in them. Then we can shine, right? Because then we can have some benefits. Then for Ruby and R, actually these numbers might be already old. I think they're already even better on these languages. So for Ruby and R, we can really provide a performance benefit over what is currently there, and a pretty significant one. The reason is, of course, that Ruby has not seen a lot of investment in terms of cheat compilation technology. There has been MRI still an interpreter. It can be like 10x, 20x faster than MRI in particular on simpler benchmarks. Then there is JRuby actually as the fastest version right now, but we can be this 4.1x speed up is versus JRuby here. So this is not versus MRI, because MRI will be at 10x or more. So Ruby is really something where we can provide a lot of speed, and we actually think that for Ruby the speed might be necessary to compete with JavaScript, because Ruby has seen recently a little bit of a drop in attention versus Node.js. But I think we can potentially help here Ruby to catch up here, because JavaScript got all this industry investment with Microsoft and Firefox battling versus Apple and Safari on the JavaScript performance front. So on JavaScript, we can also be competitive with the latest and greatest of JavaScript. Maybe we're a little bit slower, like this is 10% slower here. This is on a selection of the Octane benchmark suite. So that's the benchmark suite that was published by Google. That is a very CPU-intensive JavaScript benchmark suite. But we can run even JavaScript here competitively in Graal. And as I said, these numbers are very rough numbers. On some we are better, on some we are worse. It very much depends. On JavaScript, it's actually similar to Java, which means the more complex and modern JavaScript idioms you're using, the more our chances to actually beat V8 or Firefox. Because those JavaScript engines are around for a longer period of time, so all the code patterns they will be for sure very nicer. But the newer code patterns, like newer ECMAScript 6 patterns, sometimes they are completely bad on it because you just didn't have the time and investment to implement. But in general, our system actually, one of the benefits of our system is that we can, because like Truffle allows a very simple way, a relatively simple way to implement a language. You don't need a big team for it, you don't need like a new compiler for it, you just implement a language as an interpreter. So this allows us to be better on some of the corner cases, because we do not need to modify 3 different JIT compilers if we want to make a corner case faster. We have one place we can just optimize it. So R is a statistical language that's very important in the statistical domain, and therefore also very important to Oracle, of course. And for R, the situation is also that R at the moment is only interpreted language, so there's only an interpreter for it, which means we can, for scalar code actually, we can be up to 100x faster. Because R is not really designed for scalar code, but even for vector code, we can be like 2x, 3x, 4x faster than the fastest version of the R interpreter. R actually, the story is that people, even for Ruby it's similar, I think, that people see, okay, the language is slow and they have a performance problem, and then they rewrite parts of it in C, and they use native extensions to communicate with it. And this is a very sad state of affairs, because that's not a very nice way to program, because you then have like a C program and an R program, you need to talk to each other, there's a mismatch. And we can actually execute the R code even if it's scalar code, even if it's code where traditional C is faster, we can with R execute at similar speeds. Then we have here native, which is here comparing against just C LLVM, it's C compiler, and when executed on our system versus ahead of time compiled. So also there we are kind of a little bit slower, but in the ballpark, so not an order of magnitude slower. And the nice thing is, all of this is achieved on the JVM. So all of this is achieved on the same virtual machine, and all of this is achieved with the same compiler, with the same Deutsch collector, and it is achieved in a way that allows those languages to actually interop together. Right? So they can actually talk to each other. So, because nowadays, it seems like the world has settled on, if you talk to each other, you need to serialize to JSON and deserialize from JSON. So we are kind of still somewhere in the, I think, basically put it down into ASCII and get it back from ASCII. That's the way to interop, which is not necessarily the most efficient one. So we can have interop between these languages. And one small slide I still have here on project Sulong and the LLVM-based stuff, because I just want to share a little bit how it works. So we take here some function written in C or Fortran or some other language. And we can compile that with the LLVM frontend, with the Sulong frontend to LLVM bitcode. And this is then the bitcode we interpret with Graal. And one reason for us was really to have also LLVM-based languages available on the JVM. There is one other reason here is we actually providing here two ways of execution. One is a way of execution where you just execute very similar to as if you would have time compile. And there's a second way of execution where you execute sandboxed. So you can then sandbox your LLVM bitcode execution in a way that avoids buffer overflows and similar potential security problems. And of course, you can then also use the language interoperability. So interoperability means also for us a way we have no performance barrier between the languages, which means we can inline one language into another language. So these are ESTs of various languages, and we can inline them. I have here a small example that is a JavaScript method here, and it is here defining the add function of the sum method in Ruby. This is a Ruby definition, and then also in Ruby you explicitly export this add function. So you kind of have like a domain where you can export symbols to. And here you can import the symbol, add symbol into JavaScript. And then you can call this add as if it would be a JavaScript function. And well, the important thing is when this function is compiled to machine code, the machine code will look like this, which is the smallest possible machine code you can get out of there. There's no overhead whatsoever. It's adding up to sums, it's inking, and some jump is overflow to some, well, because this is the deopt, right? Because we de-optimize if we would overflow in the sum here. Because we need to speculate that we can represent this value as an int value and not a double value, right? But it's kind of compiling all of the overheads away into a very tight assembly code, even though there is two languages involved here, JavaScript and Ruby. So mixing JavaScript and Ruby does not occur so often in practice, because either you're like a follower of one religion or the other. But what happens more in practice is, for example, mixing native code and JavaScript, or mixing, And here I have one example where you can define a struct in C, and then you call a JavaScript function. And the important part here is that the conversion of the data is not happening at the function boundary. So it's not like you're here, you change the data formats, and then suddenly A becomes a JavaScript object. That's not how it works. The way it works is that this is still a C pointer, and it's loading into JavaScript land. And only at the point in time when JavaScript then accesses properties of the C pointer, it would then get the values out and would actually access the values according to the C layout. This allows you to have data structures in one language and then access them from another language. This can also, in the long run, for example, allow you to have your own efficient way to represent the data structures in C, right? But then you want your programmers to program in some very high-level Ruby, JavaScript, whatever language, because it's nicer to express maybe the algorithm in that language. But you can express the data structure in one language, algorithm in the other language. And the way this works is that the languages, like the objects, carry around the metadata with them, like what their structure is, and the language doesn't need to know about them. one very important aspect for us in this multilingual domain is to be able to execute C extensions of languages or native extensions of languages, because most of the languages unfortunately have a fairly not very well defined native interface. So Java is actually a very nice exception because GNI is well defined, small, you can do something about it. But for example, well, Node.js doesn't have a native interface yet. The native interface is the header file of the V8 JavaScript engine. It actually gave them a lot of programs over the long run because that header file was changing more frequently than they liked to. Okay. Which is also the reason why if you have actually a Node.js module with native components, you need to make very sure that the version is matching. You're now trying to undo that mistake by introducing something like that. But yeah, let's see if that will work for now. Ruby and ARM is in a similar state of affairs, where native interfaces do not exist. It's more like the header files of the engine is the native interface. And this, of course, leads to not so nice compatibility issues. It's like as if you would export every symbol of hotspot to a Java application. That will not be pleasant. And but one way for us to still execute some of this, because this actually gives us the issue that we cannot so easily swap out the implementation. And this is one of the biggest challenges for the project, in particular the R and Ruby space. It is that we need to be compatible with the reference implementation. And the reference implementation does not have a clear specification, does not have a clear interface. So that takes a lot of manpower and a lot of very test-oriented engineering to get the compatibility to a level that it works in practice good enough that people can switch the engine. It's kind of like a little bit of a lock-in that they're doing there by exposing everything. So yeah, this is actually one of our one impressive speed up slides from Ruby. I think actually the numbers might be higher nowadays. So this is conservative. We were doing here some experiments on an image processing library that was written in Ruby, but the library was also later ported to C, or parts of it ported to C because we were not having the best performance. And we can do about 8x, maybe 10x faster on the Ruby parts. And this is versus C Ruby, so this is also an interpreter. So an interpreter is easy to beat. But then, even if the interpreter is kind of enhanced by the C extensions, so part of it is now running in C, part is running in Ruby, when we can actually run the Ruby code fast and the C code fast, and can even sometimes inline across those two boundaries, we can get further speedups. So our ability to inline across boundaries between C code and Ruby code is helping us here to obtain even more speedups for Ruby, in particular, even if the application is sped up with C extensions. And we have a similar experience with a recent R project that we did on the larger R algorithm. Right, so the project is open source available, and there is the Graal compiler open source available. So this is Java compiler I was writing about on GitHub. There is the Truffle language implementation framework available, which is the language implementation framework that the R, Ruby runtime, JavaScript runtime are depending on. There is the fast R runtime available open source. That is the runtime that is depending on Truffle here, and that's implementing R. There is also the Sulong project, which is the project for running LLVM bitcode open source available on GitHub. And our Truffle Ruby implementation is currently part of the JRuby repository on GitHub. There is actually recently, most of a large chunk of the activity on the JRuby repository was done by these Truffle Ruby implementers. Yeah, so you're welcome to look at these projects, ask questions. There is a Graal dev mailing list also on OpenJK. And there is a Git chat room on Graal core. And yeah, you can actually also, if you like to you can do some experiments with Graal core, because you can like run it with a pre-built JDK. So you just need to run, like, it's like compiling a Java project. You compile Graal, and then you can run it with a pre-built JDK, and you can potentially modify the compiler or play around with it. So there is also pre-built binaries of Oracle JDK available on the Oracle Technology Network. And we are also at the moment in a stage where we can work with early adopters, with companies or institutions that would like to test their environment in the context of Graal. We've already several users also within Oracle, but we're also interested in getting some early adopters who think they can maybe give us some feedback or see whether their environment can run faster on the Graal compiler. Alright, so that was the core content of the talk. This is a very big list of acknowledgements because there's a lot of people involved in the project. Various people at Oracle, Oracle Labs, also at various universities. There is at least 2 Italian people here, which is Daniele Bonetta and Danilo Anzaloni, who have been PhD students in Lugano, and after that joined our team in Linz, and Danilo is now in Zurich. Yeah, we are actually also looking for PhD students for the project. So there's one open PhD position right now on the project in Linz. So if you happen to have connections to universities or have a very motivated master student who wants to do something in this space, we are interested in hiring there. Right, that was the last slide. And with that, I'm open to answer your questions. Thank you.
I wanted to ask if the new optimization introduced in the new JDK also includes the take call optimization.
Right, so the question is about tail call optimization. So we do not, in Graal, do not offer tail call optimizations. It is possible to do tail call optimizations via Truffle. So if you have a language, we actually did experiments with that. We were doing a little bit of a closure prototype. And you can, the Truffle framework is powerful enough to do a tail call optimization. Because the way you would do it is you program it with exceptions. Actually, in Truffle, even control flow in languages, non-local control flow in languages is programmed with exceptions. Like if like Ruby or JavaScript, you can sometimes return over multiple AST nodes, then we throw an exception, we throw a return exception. And this is optimized very heavily in the compiled code, so it becomes just a jump. So it becomes effectively not and the exception is escape analyzed away and so on and so forth. Right? So there's no overhead. And tail call optimizations can actually be done in Truffle in similar ways, where you throw the exception and catch it and then do the call, and then in the end it can be compiled by Graal to a loop. So we have we did some demos on that, but yeah. So actually if you have a language that would heavily profit from that, yeah, it can be done on.
Thank you.
And how is changed the memory overhead on the compiler phase if you have a Java code for the compiler part?
Right. The question is how the memory overhead of the compiler is given that the compiler is written in Java and how that influences the overall memory that you have.
It's an important issue.
Yes. So of course the compiler is allocating its data structures on the heap, which is the same place where the application is also allocated. That can give some amount of cross inference. However, there is 2 aspects here. One aspect is the compiler's data structures are all short-lived. So the compiler is usually, it's not like a compiler would get the data structures very long. It's like after each method compilation, everything is dead, right? So the compiler data structures, the compiler does not hold any significant amount of data structures live over compilations, which means all of the compiler data structures should be dead very, like in the young generation. So they shouldn't get to all the generations and therefore not influence the behavior too much. The second aspect is that usually when you have a server style application, your heap or your data set might be a couple of gigabytes, and the compiler's data structures of compiling a method is maybe between 10 and 100 megabytes. So it's something that's really not very significant compared to the live data set of the application. And we do performance measurements on SpecShip 2015, which is one of the larger JVM benchmarks, and we do not see any disadvantage for us compared to C2 in terms of because of this memory sharing. Also, all of the numbers for Java and Scala, we run with the same heap configuration, right? So there is no, like in our experience, running benchmarks, running workloads, it did not influence. But if you're very GC sensitive, it could have an influence. Right, Chris?
That's the things that I'm worried about for trading systems or something similar, because now you have not only the process introduced by your application, but by the compiler too.
Right. So, if you have something like a high-frequency trading application like Deutsche Bank has, they don't have allocations. So they have zero allocations. At the point in time when you have zero allocations, it doesn't matter when your compiler allocates or not. And the other aspect of this is that if you have a high-frequency trading application, what they would usually do is they would initialize the application in the beginning with some example workloads, and then disable the compiler after some time, or say well, now my application is stable, right? And then there should not happen any compilation afterwards. And this is the other aspect of why this might not matter so much, because it's rare that there will be a compilation in the later phases. Compilation usually happens a lot at the beginning, not so much in the later phases.
And another question. In the last conference, I watched from Azul. I watched they introduced a mechanism to save the profiler results and then reuse them to have already warmed code. Do you think that it's possible, or there is a plan to introduce something similar?
Yeah, at the moment no plan for that, but it's very easily possible. It's not a problem at all. Right? When we throw our profile data from the hospital in Java, we have it in CLS form, so we can kind of fix it. One thing that goes into that direction is we have, it's not active, but it's a prototype that does full weekly compilation for Graal. Because that's one of the aspects we want to enable before we go in production at some company. Because when you have a failure, we want to be able to replay the whole compilation process. And Graal actually allows this to a certain extent, because Graal is capturing the outside world via Java applications, via Java objects, Java interfaces. So you can do interface proxying and kind of fake up the interfaces at a later point in time. You don't necessarily need it. So that's the goal there. So regarding this thing about there's one project which I didn't have today on the slides, which is called Substrate VM. You might have heard about it.
So repeat the name?
Substrate VM. Substrate VM is, we call it Substrate VM because we wanted to build the minimum substrate to run Graal, like the minimum set of things that runs Graal. And this project is using Java ahead of time compilation. So it takes a Java application, in this case Graal, which is a Java application, and fully ahead of time compiles it to machine code. And then it has its own memory management system there, it has a GC there. And what we achieve in this setup is that we achieve very low start times, which is interesting potentially for Ruby or JavaScript. Because suddenly you go down from this 300 milliseconds of VM initialization, plus then the problem which is compiling the compiler, you go down to like 10 milliseconds. Because suddenly you don't have these problems anymore, and all the weight from hotspot. And the other aspect of Substrate VM is that it's embedded. And one possibility that we thought about when, in case this Java heap sharing with the application would be a problem for Graal, we could have Graal time compiled with Substrate VM, and then embed Substrate VM in hotspot. And then Graal would have its own heap and its own, it actually would also make the startup problem go away because suddenly Graal is pre-compiled, right? But then Graal becomes more like a C compiler written in Java, and a C-based compiler written in Java and embedded. Right? So that's actually our theory for potentially. But I mean, for this high-frequency trading stuff, for example, it would also be interesting to just use Substrate VM to ahead of time compile that whole high-frequency trading application. Because you have written it in Java, but it's compiled ahead of time compiled, it's fixed. You don't need to fix your profiles anymore. It's all time. So yeah, so Substrate VM is kind of our line of research right now that tries to attack that problem in the long run. But for a lot of configurations, I think it will not matter too much.
So let's suppose I want to implement my own language. Is there something in Graal or probably Truffle that can help me to achieve this? Or
Yes, absolutely. So Truffle API, there's actually tutorials on the web for Truffle API language implementation. There is one language that we call simple language, which is it's like a little bit of a stripped down JavaScript dialect that shows some of the main concepts. Yeah, so that would be the main starting points. Basically, downloading simple language, making it compile. You can ask questions on the GitHub chat if there's any issues, and then you can adopt simple language to be more like your own language. But I mean, it's sort of easy to implement the language on top of Graal, but it's still like, I mean, implementing language is always.
so Truffle is a wrapper on top of the Graal.
Yeah. Truffle is kind of, it's a set of interfaces that language implementers should use. Language implementers should not interface directly to Graal at all. They don't need that. They can go to the Truffle API. And the Truffle API really has primitives for a lot of stuff. You get your super fast hash map based object model for free. Like, it's actually an object model that we share between Ruby and JavaScript and R. This is actually the only serious dynamic object model that's shared between multiple languages, because it's a lot of work to do that. So you can actually piggyback on a lot of this infrastructure. There's a lot of profiling already predefined, and there's some idioms that you can look at when implementing simple language. But it's like we don't see Truffle as something that it would be like hundreds of languages on top right now, but more something where it makes it easy to really professionally implement a language. So you don't need a JVM team. You don't need a compiler team or a V8 team for implementing a language, but you still need a serious amount of effort. But you get not just to like 2x, you get to the best. You get to the absolute bottom. Your language will be competitive with the best available. So I think it's more an appeal to potentially companies that have some sort of language implementation teams, and that want to really. I mean, there's also researchers implementing languages on top of Truffle, but they usually don't cut all the corner cases. It's a very different thing whether you implement it as a researcher language. In terms of Truffle languages, one of the obvious languages that we're still missing is Python. And we are actually thinking about adding that. We have a research project with the university that did a Python interpreter proof of concept. But we are now thinking of doing Python more seriously, because Python is becoming a contender of R in the data science space, and we don't want to miss that. There is one thing which is more Oracle related, and which is one of the reasons why Oracle is, thinks our project is very important and valuable, is that we are also researching ways to integrate that project or this language execution into the Oracle database. So we would basically then be able to run the languages not only on the JVM or in this embedded form, but also as part of the query process. So this is more the Oracle-facing aspect of this project. But yeah, the JVM-facing aspect of the project is really about the vision to make the JVM platform accessible to a lot of other languages and make it accessible in a way that the languages do not have like second-class performance on it, but have like absolute top performance. That's the promise, or that's the vision of the project, and so far it looks like we can actually deliver on that promise.
So another question, and how do this technology compare with the Java scripting engine? Do you think that in the future this technology could replace it or merge?
You mean Nasr?
Yes.
Yes, so there is a bytecode generating scripting engine in JVM which is called Nasr. It was done by a different team. Some of the team members, or the main team members of the team, have left Oracle by now, unfortunately. And yeah, so we think that our JavaScript engine could be an alternative or a potential successor to this engine, but it's not in our power to make such a call. It's like this is the call of the Java product group, whatever they want to ship. Yeah, but it looks at the moment like this could be a possibility.
So if I'm starting a project based on Nation, maybe it's better if I could think about the technology instead of investing on Nation.
Well, we would very much invite you to build on our technology. That's what I can say. And yeah, we think that might be, we can talk about what type of project you want to start, but yeah, depending on what type of project, it would be better to start it on our technology.
Do you have an estimating time when you will release to the public the substrate VM?
No. We do not have expected release dates for substrate VM. We also do not have fixed release dates for Graal right now, because it's like a research project going into production.
Yeah, but that's already open source, right?
Yeah, that's already open source.
While substrate not yet.
Yeah, substrate VM at the moment is not open source. We might make it open source, but yeah, there is no clear date on that. One main aim we have for the project is to have a fully functional open source Graal VM. So something, because there's also one of the languages that's still missing in the open source is JavaScript, which is actually one of our main languages. And it is based on our internal testing the most complete JavaScript engine available right now, because JavaScript has evolved very fast with ECMAScript 2016. So we are passing more tests than V8 or Firefox on ECMAScript test 262. So it has some, it is getting fairly complete and strong. But we don't want to release something half-baked. We don't want to put something out there which is like, only second best, because people look at it and say like, oh, yeah. There's a first impression to be made, and we want to make that impression in a good way. One thing about JavaScript which you didn't mention in the presentation is that we are supporting Node.js. So it's not just JavaScript. We do support Node.js. There was a project from Oracle based on Northorn for supporting Node.js, which was called Avatar.js. That project unfortunately stopped. And we are supporting Node.js. We have a different approach. Our approach is based on emulation of these V8 APIs. And this means that you can also run native Node.js modules on our system. So it will be really fully compatible.
So
also precompiled modules, native modules.
Yes.
So
You need to recompile them against our header files. That's all. It's a little bit similar like what Microsoft did with Chakra Core. We also have integrated this Node. We have integrated our JavaScript engine also with Node, and we can.
So you bind to native code. You're not compiling. You're not using the LLVM in that case.
We're not using the LLVM backend in that case. We could actually do that in the long run, but for this project, because the LLVM project is still not so stable, we want to ship with it. We are using something that we emulate the header files, which works out fine in terms of compatibility. We are still fixing some performance issues where sometimes this boundary is crossed too often, and then we need to start doing some tricks. But the main aspect of it, and this was very important for us, is that we can ship with an unmodified Node.js distribution. It's basically you take Node.js, you rip out V8, and then we ship that. This is actually one of the more interesting aspects of the project to some of the groups or companies we're working with, because then it allows you to do some Node.js application, but still leverage all of your investments you made in Java, and you can have direct interoperability between your Node.js application and your Java. Yeah, but we are also in the Node.js space. One of the biggest issues for us is compatibility. So we have a lot of testing infrastructure. We are testing at the moment, I think, the 1,000 most, no, actually testing the 200 most downloaded Node.js modules. But those modules have a lot of dependencies. So we automatically testing also the dependency tree. And we're running about 110,000 tests on each commit there, which are all Node.js tests. But it's not enough yet. We need to actually scale it up. Because it's like just very small, subtle differences can mean a big difference in terms of test results. The difficult thing, among other aspects, is that the tests of a model is sometimes more complex than the model itself. Because the tests are sometimes using reflective features, or they are doing some funky tricks, or they are looking at stack traces and their format. And then this needs to be like letter by letter the same. Right, any more questions? If not, then thank you again for your attention, and